Lecture 7, Buffers. Alright, so let's take a look at Chapter 19.1, Buffers. Well, what is a buffer? Buffers are solutions that resist changes in pH due to the addition of strong acids, the addition of strong bases, or volume changes. So buffer solutions will contain a weak acid and weak base. Now let's take a look at a weak acid and a weak base. Here we have a weak acid and a weak base. And this solution is called PBS, which is known as a phosphate buffer system. So now, how do we know which one's a weak acid and which one's a weak base? Well, let's get started. So we have HPO4 2- plus hydronium goes into H2PO4- plus water. Well, we know that hydronium, right here, is a strong acid, which I'm going to symbolize as SA. And because our hydronium is our strong acid, we know that HPO4 2- must be our weak base. Now, its conjugate, H2PO4- means it has to be the acid, and because a weak base needs to have a conjugate weak acid, H2PO4 is also our weak acid. So let's break apart H2PO4. Alright, here we have H2PO4-, OH negative, which is our hydroxide, HPO4 2-, and water. Well, since we know hydroxide is a strong base, for example, sodium hydroxide, we're going to call this strong base. Well, because we know H2PO4- is not one of our strong acids, it's going to be our weak acid. Then again, we look for our conjugate. So we have HPO4 2- as our conjugate. And because a weak acid needs a conjugate weak base, we know that this is our weak base. Now here's a question. For us to solve the pH directly instead of calculating hydronium, because hydronium usually refers for a strong acid, first we need to use the Henderson-Hasselbalch equation. So how do we get this equation? So let's take a look. For any weak acid, which we represent as HA, the dissociation equation and Ka expression are as follows. So our dissociation equation is HA plus water goes into our base plus our hydronium. Now for Ka, we're going to show our hydronium times the base all over HA. Remember, water is a pure solvent, so we do not need to represent that into our Ka expression. So next is the key variable that determines hydronium is actually the concentration ratio of the acid species to base species. So when we rearrange to isolate hydronium, we get hydronium is equal to the Ka times the acid all over the base. Next, we're going to take the negative common log theorem on both sides to give us the negative log of hydronium is equal to the negative log of Ka minus the log of the acid all over the base. So let's simplify this a little bit more. So we know that the negative log of hydronium will give us a pH. We know that the negative log of Ka will give us a pKa. Well, then because of the nature of logs, we can invert the buffer component concentration ratio, which is the acid over base, and the sign of the log can change. So let's change the sign. So when we change the sign, we need to flip the acid and base to give us pH is equal to pKa plus the log of our base all over acid. This is known as our Henderson-Hasselbalch equation, which we saw in Chem 100. Now let's do an example. Alright, so the first thing we need to do is we need to identify what type of acid and base we're working with. So here we have acetic acid. Acetic acid is a weak acid, so that means its conjugated base must be a weak base. So then we know we're going to be using the Henderson-Hasselbalch equation. The next thing we need to do is we need to use our book, Appendix C. Appendix C is going to have our Ka values. Now the Ka value I can find is of acetic acid. So it's going to have a Ka which is equal to 1.8 times 10 to the minus 5. Because I'm using the Henderson-Hasselbalch equation, I know I need to find the pKa. So to do that, I take the negative log of that Ka and I get 4.74. Now remember sig figs. If I have 2 sig figs in my concentration, I need 2 sig figs after the decimal point. Now because I do know the molarities of my acid and the molarity of my base, I can now plug into the Henderson-Hasselbalch equation. So here we go. So I get pH is equal to 4.74 plus log of 0.10 over 0.10. Well, 0.10 divided by 0.10 is going to give me 1. Well, the log of 1 is 0. So my pH is going to equal 4.74, which is also equal to my pKa. So in general, when your acid concentration is equal to your base concentration, your pH will equal your pKa. So remember, a buffer resists changes in pH of weak acids and weak bases. Let's try another example. So if I was given acetate, which is the base of acetic acid, with a molarity of 0.2 molar and acetic acid 0.1 molar, what do I need to do first? First thing I need to do is find the Ka value. So again, the Ka value for acetic acid is going to be 1.8 times 10 to the minus 5. I'm now going to look for the pKa, which is taking the negative log of the Ka to give me 4.74. Now I can use this to plug it into the Henderson-Hasselbalch equation, which I'm going to do, plus the log. Remember, it goes base over acid, and I'm going to get 5.04 for my pH. Because the pH is less than 7, I know that my 5.04 means I'm in an acidic solution, but on the basic side of the pKa, as we can see right here. So 4.74 means that this pH is more basic than my pKa, but the pH means it's an acidic solution, but very weak. Now let's do another example. So again, we have acetic acid and acetate. So the Ka again is of the acetic acid of 1.8 times 10 to the minus 5. Again, I take the negative log of the Ka to give me a pKa of 4.74. Now again, I'm going to plug this into the Henderson-Hasselbalch equation to give me this, 4.44. So again, this is an acetic solution, but it is more acetic than the pKa. So my pKa is 4.74, which is greater than 4.44. So that means my pKa is more basic than my pH, or my pH is more acidic than my pKa. So in general, when our base concentration is equal to our acid concentration, our pH will equal our pKa. Now when our base concentration is more than our acetic acid concentration, then our pH will be greater than our pKa, or our pH is more basic than our pKa, or our pKa is more acidic than our pH. When our base is less than our acid concentration, our pH is less than our pKa, or our pH is more acidic than our pKa, or our pKa is more basic than our pH. Now remember, When we use a conjugated acid-base pair that has a pKa, we want it within plus or minus 1 unit of desired pH. Now, how do we find the ratio of our acid to base? Well, we take the Henderson-Hasselbalch equation, pH equals pKa plus the log of our base all over our acid. And what we do is we rearrange this equation. So the first thing I'm going to do is I'm going to take the pKa and subtract it from the pH. So then I get pH is minus pKa, which is equal to the log of our base all over our acid. Now, to get rid of logs, we know we need to take the 10 of. So if I take the 10 of, gets rid of the log, so I need to take the 10 of the pH minus pKa to give me 10 pH minus the pKa will equal that base over acid ratio, which is cool. Now, let's actually look at an example of this. Alright, so what buffer component ratio is needed to make a pH of 5.0 of acetic acid and acetate buffer? First thing I need to check for, is this a weak or strong acid base? This is a weak acid, weak base. Great, so I know I can use the Henderson-Hasselbalch equation. Next thing I need to do is look up the Ka value for acetic acid. And I know that for acetic acid is going to equal 1.8 times 10 to the minus 5, which is going to give me a pKa of 4.74. Now, next step is I'm going to put the Henderson-Hasselbalch equation down. So pH is equal to pKa plus the log of my base all over my acid. Oops. Alright, because we are looking for the ratio, I'm just going to plug in what I know. So first thing I know is I have 5.00 for my pH minus 4.74 is equal to my log of my acid all over, my base all over my acid. Now remember, I just subtracted the pKa from the pH, so I just moved it right over. Now, because I want to get rid of the log, I need to take the 10 root of, so I'm going to take the 10, 5.00 minus 4.74 to give me that acid-base ratio. And I'm going to get a ratio of 1.8. So that is the ratio of the buffer component to make acetic acid to acetate buffer. Let's do another example. Alright, so what buffer component ratio is needed to make a pH of 8.0 of potassium H2PO4 over K2HPO4 buffer? Well, the first thing I need to realize is this is a phosphoric acid that has potassium to it. Now, phosphoric acid is a polyatomic acid. That means it's going to have several different Kas. So let me show you. So looking at Appendix C, I can find that phosphoric acid going to H2PO4 minus has a Ka of 7.2 times 10 to the minus 3. Now when we take that H2PO4 minus and then we dissociate it with water, we get HPO4 minus, but it has a Ka2 of 6.3 times 10 to the minus 8. Now when we take that HPO4 minus, dissociate it with water, we get phosphate. And we get a Ka that's equal to 4.2 times 10 to the minus 13. Now, which one can we use? Well, we need to look at the buffer. So we know we have KH2PO4 and K2HPO4. Well, when we get rid of the cation, we are left with H2PO4 minus over HPO4 2 minus. So this is associated with Ka2 because it has my acid, and it has my weak base, H2PO4- and HPO4 2-. So it's exactly what we're looking for. So when I'm using this equation, I'm going to be using the Ka2 of phosphoric acid. So remember, anytime you are working with a polyatomic group like phosphate, carbonate, like those where they have multiple dissociations, you need to know which Ka or Kb you're going to be using. So again, I'm using Ka2, which has 6.3 times 10 to the minus 8. I'm going to find its pKa by taking the negative log of the Ka, and I'm going to get 7.20. Now again, I'm going to use the Henderson-Hasselbalch equation, so pH is equal to the pKa plus the log of my base all over my acid. I am looking to find the ratio, so I'm going to subtract the pKa from the pH. So I have a pH of 8.0 minus 7.20 is going to equal to the log of the base all over the acid. I'm going to take the 10 root to get rid of the log, and I get my ratio to be 6.3. Now let's do another example. Alright, so what concentration of hydrogen phosphate, HPO4 2-, would be needed to make a pH 8.0 buffer if we have 0.15 molar? So like our previous problem, I'm going to be using Ka2 that I found from Appendix C because I'm using hydrogen phosphate and I'm using H2PO4-. So again, Ka2 for the for it was 6.3 times 10 to the minus 8, and it gave me a pKa of 7.20. Alright, so now I'm going to set this up like I normally do. So Henderson-Hasselbalch equation, so my pH is equal to the pKa plus the log of my base all over my acid. Now because I know my pH and pKa, I'm going to subtract them. So I have 8.0 minus 7.200 is equal to the log of my base all over my acid. Now this H2PO4 I know is my acid because it has more hydrogens and less negatives than the hydrogen phosphate. So I'm going to plug that in after I take the 10 of to get rid of the log. So I have 10 of 8.00 minus 7.20 is equal to my base all over that concentration of my acid. So then I'm going to take this number, which we know is 6.3, and I'm going to multiply it by 0.15 molar to get me my base, which I get as 0.94 molar, which is my HPO4 2-. So now let's talk about steps in actually making a buffer solution. So the steps in making a buffer solution. First, choose an appropriate conjugate acid-base pair. The pKa of the acid should be within plus or minus 1 unit of the desired pH. Now you want to calculate the needed buffer component ratio. So that would be the 10 to the pH minus pKa is equal to the base all over the acid. Now to make a buffer, you need to mix together appropriate amounts of the base and acid. You're going to start with the solution of the acid, for example weak acid, and you're going to add a strong base, maybe like sodium hydroxide, to generate a weak base component. Remember, the weak acid needs to be plus or minus 1 equivalence of the weak base. Now we can do the same thing with if we start with a weak base and then we add a strong acid. For example, we can use hydrochloric acid. We will make a weak acid. Again, we need to have a 1 equivalency. So let's take a look at another example. Alright, so how many grams of potassium hydroxide would need to be added to 1 liter of 0.20 molar KH2PO4 solution to make pH 8.00 solution? Well, the first thing I'm going to do is I'm going to make a balanced equation. Alright, so I get KH2PO4 plus potassium hydroxide will give me KHPO4 2- plus H2O plus K positive. I'm going to be focusing on the anions, and I'm going to look at those that are conjugates to each other. So the first conjugates I see are the phosphates. So here I have KH2PO4, which we know is H2PO4 when we get rid of that potassium, and then we have HPO4 2-. Now we need to identify, is this a weak or strong acid base? Well, it's not one of my 6 strong acids, so it's definitely going to be weak. Now I need to identify which ones are going to be my weak acid and which one's my weak base. Because H2PO4 has more hydrogens to it than my HPO4 2-, I know that this is going to be my weak acid and this is my weak base. So if I have a weak acid, weak base, I'm looking at a buffer. That means I'm looking at using the Henderson-Hasselbalch equation. One thing I do need to figure out is I need to find the Ka. So we saw this before, because we're looking at H2PO4- and HPO4 2-, we're using Ka2 of phosphoric acid. And the Ka2 again was 6.3 times 10 to the minus 8, and I'm able to get a pKa value of 7.20. So now I'm going to find the buffer component ratio. So here we go. I'm just going to quickly just put it in. So it's my base all over my acid is going to equal 10 to the pH, which is 8.00, minus 7.20, and I get my buffer component to be equal to 6.3. Alright, now that I have that, I need to find how many moles of KH2PO4 I actually have. Now, why do you ask? Well, I'm going to set up a reaction table. And the reason why I'm using moles is because I'm looking for how many grams of KOH I need. So this is the quickest way for me to get from molarity to moles to grams, what I'm going to do. So my next step is to take the 1.00 liters and multiply it by the concentration of KH2PO4. And I'm going to get 0.20 moles of KH2PO4. Now the next step I'm going to do is I'm going to make up that reaction table. So I'm going to have my concentration, my balanced equation, my initial change, and what happens at equilibrium. Alright, so first thing we know is our KH2PO4 is initially at 0.20 molarity. For this point, we're just going to leave it in moles because we don't need to do that concentration anymore. We know that we started with something for KOH because we were asked for, well, how many grams did we use? So we know we started with something. And then we know the KHPO4 2-, we didn't start with anything, same with the water. Now the change. Well, what happens is we we break up the KH2PO4 and the KOH to actually form KHPO4 2-. And again, we know water does not really form because we don't create it in our Ka equilibrium constant. So water, we know, becomes nothing. So let's bring everything down. What happens at equilibrium? So we get 0.20 minus x. Our KOH is x minus x, so it's 0. And our KHPO4 2- gives us a plus x. And we know water is nothing. Alright, so because this is a weak acid, let's start figuring things out. Here we go. Alright, so from our setup of our reaction table, I get HPO4 2-, which is my base, all over my acid, H2PO4- is equal to x all over 0.20 minus x. Alright, so we know that my ratio is 6.3, so it gives me x all over 0.20 minus x. And now I'm going to multiply this by 6.3, so then I get x is equal to 6.3 times 0.20 minus x, which gives me 1.26 minus 6.3x equals x. I'm now going to add 6.3x to this side, and that's going to give me 7.3x is equal to 1.26, which gives me x is equal to 0.17 moles of OH minus. Now you're probably wondering, hey Teresa, can't I just get rid of this minus x? No, because remember, this x from our reaction table represented HPO4 2-, and this 0.20 minus x represented H2PO4-. Alright, now that we have moles of OH, let's find the grams of KOH. Alright, so doing a little bit of grams and moles to moles, I'm going to take my 0.17 moles. Alright, so we have 0.17 moles of hydroxide. We're going to use the mole ratio, 1 mole of KOH to 1 mole of hydroxide, and we're going to multiply by the molecular weight of KOH, which is 56.11 grams over 1 mole, to give us our answer of 9.7 grams of KOH. Remember, we're going to use the smallest significant figures, so that's why it's 2 sig figs. Alright, so this ends our buffer solutions. So now we're going to continue on to 19.2 in our next lesson. So for the assignment for this section, I want you to read chapter 19, section 1, and then I want you to do problems 2, 11, 17, 21, 23, 27, 31, and 35, just to give you some more practice. So again, our next lesson is going to go into titration curves, where again we're going to see buffers.